We're going to continue talking about dependency parsing, but instead of building the parse from the bottom up using chart parsing like we talked about for constituency grammars, we're going to look at a different formalism where we draw the edges between words as we go along the sentence. This is not only efficient, but it's also cognitively plausible. It might be how a human might process sentences to build up a syntactic structure, because this can happen as you pass through a sentence. And it also has some advantages in practice. It's better at capturing the interactions of short-range dependencies between words compared to arc-factored models that might get confused at long distances. So let's take a look at how this might work in practice. Let's say that you have a sentence like, economic news had little effect on financial markets. And you start going through the sentence. You see economic and then news, and then you realize that you can attach economic to news. Then you can attach had to news. Then you can have an edge going from effect to little. Then you can have an edge going from markets to financial. And now you have attached lots of words close together, and now you can connect all of these different parts of the sentence together into one big syntactic structure. On financial markets is a single prepositional clause that attaches to the effect, so the effect is on financial markets. And then you can connect the helper verb to effect, had to the end of the sentence punctuation, and then you can connect the root to had so that you have a fully connected tree. So we've seen how this can play out in a cartoony example. Let's now go into a little bit more formally how you might do this in an algorithm. So we're going to have to introduce two concepts. We're going to have to introduce a buffer and a stack. And you can think about the buffer as the words coming at you. So you are hearing some sentence and you have to do something with it. Either you can connect words directly off of the buffer, or you can put them on a stack for later processing. And we're going to interact with these two data structures using the following operations. We can shift. So shift moves something from the buffer to the stack. You see a word come in, you realize, I don't know what to do with this word, so you move it to the stack and you'll deal with it later. You can also put in edges. And so you want to build a dependency graph completely, so you're going to have to add some edges. And the two ways that you're going to do that are, first, you can create a left edge. So an edge going from a word further to the right of another word, so an edge going to the left. And you do this by creating an edge from the top of the buffer to the top of the stack. So the top of the stack becomes a child of the buffer's next word. Or you can create a right edge, in which case you have the buffer's next word as a child of the top of the stack. Or, to say that a different way, you have an edge going from the top of the stack to the buffer's next word. And these are the three operations. You can shift, move something from the buffer to the stack. You can create a left edge, or you can create a right edge. These are the three things that you can do in this algorithm. Let's talk a little bit about what the algorithm has to do. It has to take a sentence, which is entirely in the buffer, move things between the buffer and the stack, and create edges until the buffer is empty and you presumably parsed all of the sentence. So let's go through each of the actions in a little bit more detail and see what this looks like in terms of building up a graph. So in the left action, you add an edge from the top of the stack to the top of the buffer, and then you pop the stack. And because you're creating an edge between something on the stack and the buffer, the stack can't be empty, neither can the buffer, and you also can't have the child be the root. Otherwise, the root would no longer be the root because you have an edge going to the root. So these are the conditions that have to be true for the left action. For the right action, you have to again have something on the stack and on the buffer. You pop the stack, and then you replace wj with wi at the head of the buffer. This is because you've created an edge going to the right, and we'll see that when you create an edge going to the right, you basically take that word out of circulation for future attachments. And again, just like for the left action, the stack and the buffer have to be non-empty. Shift is by far the easiest. You take one word from the buffer, you put it on the stack. Obviously the buffer can't be empty. Let's now see an example of these actions and what it looks like in practice. So we start off with no words on the stack. We just have the root node on the stack, and all of our words are in the buffer. And this is the same sentence that we had before. Economic news had little effect on financial markets. I just drew some edges willy-nilly and didn't explain what was going on. Let's now see how this would actually work in terms of an algorithm. I will tell you what actions we're going to take. In a real algorithm, you would need to decide, am I going to shift? Am I going to make a left action? Am I going to do a right action? We'll talk a little bit about how you can figure out what those actions are, but for now, I'll just tell you what the actions should be. We'll execute those actions, and we'll talk more about how, in practice, you would figure out what action you want to do next. But in this case, it's really simple. We can't do a left action, we can't do a right action. At the very beginning, you have to shift. There's no other option. So we have to take economics from the buffer, put it onto the stack. And now we're going to make a left edge. We're going to draw an edge between news, which is the top of the buffer, and economic. And you see that we now have an edge between news and economic. What kind of news had an effect on markets? Economic news. So the edge from news to economic tells us that economic is changing the kind of news that we're talking about. Okay, so now we have nothing on the stack again. We have to shift. And so now news is on the top of the stack, and news is a subject of the verb had. So we can create a left edge going from had to news. And now, again, we have an empty stack, so we have to shift. We have no other choice. And here we have a choice, but the right action here is to shift again and to put little on our stack. And so now we have two things on the stack, had and little, but little is the top of the stack. And so now, because we're going to modify effect, so how big of an effect? A little effect. We're going to add an edge going from effect to little, and so that's now a left edge. And now we're going to shift again and put effect on the stack, and we're going to shift yet again to put on the stack, and we'll shift even further. And so now we can finally have a left edge. What kind of markets did this happen to? Financial markets. So we put an edge between financial and markets, going from markets to financial, and now we can create a right edge, because on is a preposition, and the object of that preposition is financial markets, and we draw the edge to the noun in a noun phrase. So we now have the prepositional phrase on financial markets, and we again draw another right edge from effect to on. And now we have effect on the top of our buffer, and this can now allow us to connect had to effect. So had is a helper verb of effect. Effect is elaborating what kind of action is happening. So it is the child. And then finally, we're going to shift had to the stack. This allows us to create a right edge going from had to the sentence final punctuation. And then, very, very last thing, we need to connect the root to the main verb. And so now we have root on the buffer, and we are done. One thing that I hope you notice as we were going through that is that what happened with those right transitions. And so every time you have a right transition, you're flipping what words are on the stack and the buffer. And you can kind of see how this worked. We had a cascade of unresolved dependencies that we needed to figure out. So we had the prepositional phrase, we had the verb, and then we had connecting the root to the helper verb. And as we basically went backwards through the sentence, adding in these right edges, we took the thing that we had the right edge starting from and put that on the buffer because we needed to deal with that next. And as we did that, we could basically draw all the right edges that we needed to add. And so in reverse order, the right edges that we needed to add were the root to had, then we had to the sentence final punctuation, then we had the had to effect, and then on to the noun phrase and the prepositional phrase. And all of these got connected up going backwards through the sentence. And so you can think about this in kind of loose terms as you build left edges opportunistically as you make a forward pass, and then you add right edges as your brain puts all the pieces together to form a coherent, complete overall sentence. But I just told you what actions to do. If you actually wanted to parse a real English sentence, how would you know what actions to do next? So it's possible to deterministically take a given parse tree, i.e. something that you get out of the pin tree bank that's been meticulously annotated, and create the sequence of actions that would generate that parse tree algorithmically. You do this by starting with everything on the buffer and only root on the stack, so just like we had before. And then if there's nothing on the stack, you have to shift. And if the top of the stack is a child of the top of the buffer, then you make a left edge. And so that's kind of obvious. But what's trickier is that you can only add a right edge if the top of the buffer has no children that have yet to be added. And this is a way of encoding what we saw before. You can only add a right edge after all of its children have been dealt with. Because once you add that right edge, you basically take it out of circulation forevermore. And so this is basically saying that if you have to later add more children to this word, wait. You can't deal with it yet. Put it on the stack or let it stay on the stack until you've dealt with other things first. But that tells you how to create a sequence of actions given some training data, but it doesn't tell you how to apply it, say, to test data. What if you have a sentence that's never been parsed before? How do you apply this kind of algorithm to that? To parse those sentences, you need to learn a classifier that has 3 labels, each of the actions. And then you represent the buffer, the stack, and other characteristics of your sentence using features or vector representations, and you then create a 3-way classifier that decides which of the 3 actions you're going to take. And there are many things that you could encode. You can include vector representations, you can have the part of speech of the words, how much stuff is on the stack, what is the sentence position of this word. You can add all sorts of features to try to give your classifier clues about what it should do in this kind of situation. We talked about the complexity of arc-factored models and how you can parse them using the Eisner algorithm. What's the complexity of using the shift-produce parsers? It turns out to be pretty good, and the analysis is pretty simple. Each word can only go on the stack once, and that means that it can only be considered by the algorithm 2n times. Once as it goes through the buffer, once as it goes through the stack. And this is actually an upper bound because some words never touch the stack. So the complexity is O(n). And it's not that arc-factored models are better but slower. They're actually pretty different, and they have different strengths and weaknesses. And it's not just that shift-reduce parsers are faster but worse. They actually do a better job at capturing local dependencies when words aren't too far away from each other. And that's because arc-factored models get distracted by long-distance dependencies. They're considering any possible interaction between words, and they can get distracted. But by the same token, those arc-factored models do better at the big picture. They can connect verbs correctly to their arguments, and for some languages that's really important. And for some downstream tasks, for instance, looking at semantic parsing, that's critical for getting the final answer correct. So it's important for you to know about both arc-factored models and shift-reduce models for capturing dependency structures.